Hello, here we'll talk about distances and angles between points and lines in real coordinate vector space, and the means of finding them will be what are called scalar products. Misspelling it, have to start again. The motivation is computing distances or length. And let's start with the, next to the easiest situation. The easiest would be just one dimension. The distance is just the difference between the real numbers representing points on the real line. Let's imagine we have something more interesting happening on the plane. So we look between 2 points, and one I would place at the origin, because why not? And the other will be somewhere here with then coordinates A and B. So I'm choosing the coordinate system. And the distance will be the length of this. And here we know how to find it using Pythagoras. This is the hypotenuse of a right angle triangle with sides A and B. So the distance which we're after, this C squared, will be the sum of A squared and B squared. And if we look at the next case of three-dimensional space, and again imagine some coordinate system with the origin at one of the points, we measure the distance from between, and then the other points is somewhere here, so we're after the length of this segment. And then we could still use Pythagoras, but in 2 steps, could drop it down to the xy plane here. So that will be the hypotenuse. Here we'll have sides in coordinates of the point ABC. Here the hypotenuse, we'll call it U, will have a square equal to the sum of squares of A and B. And this, the distance D here, squared, is the sum of C squared, or rather we'll start with U, this base U, and then C squared. But then U squared itself from this right angle triangle, for example, is A squared plus B squared. And so total will be just the sum of squares of the coordinates. And then this sort of geometric reduction can be used in any dimension, and we end up with the statement that the squared distance, it's always easy to talk about the squared distance. So squared from the origin to some vector is given by the sum of squares of the coordinates of the vector. And it has a name. One of its names is the norm squared. So squared distance is the same as the norm. We have the answer for the norm from this formula. It's just the positive square root of the sum of squares of all the coordinates we have. So it is length or norm of a vector v, or rather x. This is simple but still not very nice expression to do computations with. Instead, we could bring it closer to the main tool we have in this topic, linear algebra, linearity. So let's look at what the first to make it more amenable, we have to get rid of the square. So let's look at the squared distance or squared norm. Let's look at this sum of squares. If we have two vectors and we compare the squared norm of the sum of these two vectors with the sum of squared norms, of course, we won't have, in general, the full agreement. That will not be true. But the deviation is nice. And, well, okay, before I will just call it twice some quantity depending on x and y. So let's see what this quantity is. We start with the sum of squares of coordinates of x and y added. So that is the sum we are looking at in here. And then we could do the arithmetic, first expanding the square of the sum. And then regrouping the sum, so distributing the summation through this sum, and we will have the sum of x's all squared, not all squared, but each of them, then the sum of y's squared, and then twice the sum of pairwise products. So that is the deviation. That's what this quantity is. It looks like an unnecessary complication. Instead of just dealing with one function, we introduce a function depending on pairs of vectors. But the beauty of this complication is that this new function is much better for doing linear algebra with. Let's call it for what it is. It's called a scalar or inner or Euclidean product. And now this function separately in x and in y is linear, so the properties are much better now than for the original function in computing length. The first bunch of properties are just saying that as a function of x separately with fixed y, or symmetrically as a function of y with a fixed x, it is linear. So the additivity is first in linearity, and then scalar property that we can take scalars out for the first argument, and the same for the second. There is no difference between the first and the second, actually. Additivity in the second argument or scaling property are still true. So together, these properties will make the function linear in each argument. Such functions are called bilinear or bilinearity. On top of that, this expression is symmetric in x and y, so if we change the order in the scalar product, we'll have the same answer. And finally, so that is symmetry. And finally, if we take the same vector in the first and in the second argument, we will have nothing but the sum of squares. So we'll have this distance squared. So it will be just the sum of squares. And as a sum of squares, it is never negative. It is always non-negative. And moreover, it is zero, so this sum of squares, if and only if all squares are individually zeros. So that means the vector being zero. And that together called positive definite. So the function which we are looking at, this function, which is called scalar product, satisfies this bilinearity property, linear in each of its arguments. It is symmetric and it is positive definite, meaning that never takes negative values when we take the same argument twice. and only 0 in this case if the vector itself is 0. So yeah, that is what allows us to compute norms if we know this function. So that's how we still be able to see distances by just computing the function, the scalar product on the vector with itself. And yeah, then a little observation before we continue to dealing with angles is that any vector can be scaled down to a vector of length 1, which will be proportional to it. So if we have a vector x, we can always divide it by its norm. And that vector, the new one, the scaling of the original, will have a unit length. Indeed, if we just compute its inner product with itself, that will be the same as the norm if the norm is 1. But yet it will be in general the squared norm. If we compute this, we will have this appearing twice. And so using scaling property for each of the arguments, we can take out the norm from the denominator inside in front, and we'll have it twice, so it will be squared. And that will be the same as the scalar product on x with itself, so the ratio will be 1. Now let's look at angles between vectors. Lines of vectors doesn't matter, we can always choose a directional vector on a line. Let's start with the easiest situation where both vectors have length 1. And then imagine one going along our first coordinate axis, y0. So the second one goes somewhere here. So this is a unit length vector, and this is also a unit length vector. We want to see what is the angle between them. If we choose this to be the first coordinate axis, then the second vector will have prescribed coordinates prescribed in terms of trigonometry. The first coordinate will be what is called the cos of the angle, and the second coordinate will be the sine of the angle. So that will be the coordinates of the vector. And then if we look at the scalar product of this vector called u and this second vector called v, so this scalar product, which we defined before, computed in this two-dimensional vector space. So it will be just the sum of coordinates, and coordinates of this vector are 1 and 0. The sum of products of coordinates, we will just have the first coordinate of v, namely cos of alpha. So that's how we can see the angle between two unit vectors. So these are unit vectors. A unit means have length 1, or rather unit vector. So these are two unit vectors, and the angle between them is just their scalar product. In general, if they are not unit, what happens? So we can always scale them down to length 1, to unit vectors. So this scaling doesn't change the angle between them. The cos will still be the same. So for arbitrary, the angle between them is, or rather cos of that angle is computed by this. Now these are unit vectors. But then if we want to see what it is in terms of actual u and v, we will have the scalar product of u and v over the product of their norms. And that is a generic formula which works all the time. So that is the more general statement. Perhaps putting it in a box is good. This is also an important formula. And finally this. That was the starting point of the whole story of measuring something in an n-dimensional real vector space. So finally, we could say, we can comfortably express the condition that two vectors are orthogonal or perpendicular. If the notation for that will be U orthogonal to V. If and only if the scalar product is 0, the 90-degree angle transformed into cos or substituted to cos will give us 0. So that is an easy condition of seeing that something is perpendicular to something else. Rest will come later. See you then.